Hey everyone, we're resuming our trig equations and identities unit, and today we're going to start something called identities. Okay, so first of all, we're going to talk about what the difference between equations and identities are. So if you had, say, something like 2x squared plus 3 equals 11, that is an equation because it's only true for certain values of the variable x. So in other words, if I subbed in 1 into this equation, I would get 2 plus 3 is 5 equals 11, which we know it doesn't. So the only value, or the only values of x that would make this equation true, in other words, left-hand side equals right-hand side, would be -2 and 2. So that's an equation. An identity, though, is something in which no matter what value I sub in for x, the left-hand side of the equation is always going to equal the right-hand side of the equation. Okay, see the difference between the two? Okay, so what we're going to be doing now is we're going to be working with identities. We're just going to skip to another page. So if you want to kind of flip to the next page, well, we can talk about these. No, these are the basic identities. We're going to look at the next page. So let's flip to there. This page here, verifying identities for a particular case, we're going to look at that more in our next lesson, but let's just talk about what that is for now, and then we'll return to it on the next lesson. Verifying is when you sub in a particular value for x, theta, whatever the variable is, and it shows, and then you work out what the left-hand side would be, what the right-hand side would be, and if you get the same answer on the left and the right-hand side, you have verified the identity. So as a result, that doesn't mean that the identity is proved for all values, but just for that one value, okay? So that's the difference between verifying and proving, which we'll get to in a second. So like I said, we'll return to this concept more on the next lesson. You don't have any questions assigned on this lesson on that particular topic. So let's look at the next page. Okay, so just to compare, we're going to be looking at proving identities, more so again on the next lesson where we're proving the left-hand side equals the right-hand side, but this kind of begins our working with identities. To prove an identity, we have to treat the left side and the right side separately, okay? And again, we'll do that more in the next lesson. You work with both sides until you get them down to equal the same thing. So don't write left-hand side equals right-hand side. Sorry, do not make the mistake of assuming the answer by writing left-hand side equals right side at the start of the proof. And this is the thing that students sometimes do. You do not move the terms from one side to the other in identity. Okay? That should never happen. Okay, and we're going to jump the basic identities thing because we don't really do that in 30-1. So let's flip to the next example. Okay, so on this next page, this is when we start getting into what we're going to be using a lot. Quotient identities, okay, and Pythagorean identities, okay. In addition to that, we also have that cosecant x is 1 over sine x. We have that secant x is 1 over cos x, okay. And we do have that cotan x is 1 over tan x. Although myself, most of the time I would use this particular identity for cotan x. All of these are on your formula sheet. So guess what? Your formula sheet is going to become your new best friend on this part of the unit. Okay, then we have Pythagorean identities. Okay, and these identities really are developed from the unit circle. If you recall, on the unit circle, right, the equation in the unit circle is x squared plus y squared equals 1, and x squared is cos squared, and y squared would be sine squared, because x is cos, y is sine, right, on the unit circle. And look at that. That's the same identity. And these two can just be developed by dividing this equation. Let me just show you that. If we divide this equation, I'll write it over here, let's say. So let's say we take cos squared x plus, I'll turn it around so we're using the version they gave us, sine squared x plus cos squared x equals 1. If we divided that by, let's say, cos squared x. Everything, both sides of the equation. If you look at that, we would then have sine squared over cos squared. Well, I know sine over cos is tan, so this would become tan squared. Okay, if they're each squared. Cos squared over cos squared is 1. And 1 over cos squared, 1 over cos is secant, so 1 over cos squared would be secant squared. And look at that. That's really the same as that identity. And this final one, guess what you would divide by on each term? You divide by sine squared to get that one. Okay, each of these identities can be rearranged. So if you wanted to use this one, but you needed more sine squared, you could subtract cos squared from both sides. And then you would get that sine squared equals 1 minus cos squared. Okay, so any of these can be manipulated based on what you need. Okay, so let's look at a further example. Okay, these are the kind of questions that you would be doing on this particular lesson. So example number 4, express each single trig ratio. Okay, express each as a single trig ratio. So a trig ratio, sine, cos, tan, that kind of thing. A single trig ratio. So if you look at this first question, we have 2 trig ratios over top of each other plus another number yet too. And then it says use a graphing calculator to verify, and I'll show you how to do that. Okay, so let's go back to this. Sine squared over cos squared. Okay, if you recall from your formula sheet, tan x is equal to sine x over cos x, right? So if I have sine squared over cos squared, that's really just each one of these squared. And we can do that by simply squaring both sides, right? Like that. Okay, so that would give us that. So we replace that with, I would prefer to work down here, but we don't have the room. So tan squared, that's what that becomes. And then we have plus 1. Okay, look at your formula sheet again. When you see squareds, okay, tan squared, whatever, that could be one of our Pythagorean identities. So if you look on your formula sheet, you'll notice we have 1 plus tan squared equals secant squared x. And that's really what we have. So we can replace all of this, right, all of this, with secant squared. So that now becomes secant squared x. Okay, so just replacing more complex things with simpler things so that we get it down to, this is a single trig ratio now. It's just secant squared. Okay, let's look at part B. Sine x plus cotan x times cosine x. Okay, when the trig ratios are written next to each other like this, that means that they're being multiplied. Okay, so envision that there's brackets around them, meaning they're multiplied together. Okay, so let's take a look at all these things. Well, I see that cotan on our formula sheet is defined as cos x over sine x. The 1 over tan x wouldn't be very useful here, so let's write that down. So cotan x is going to be replaced with cos x over sine x. That's what it's equivalent to. And then cos x, because I'm now multiplying cos x times cos over sine x, I'm going to write that as over 1. It'll be easier to work with fractions here. Okay, we'll bring this back up. So we'll have sine x, okay? So now we would multiply these two together, okay? We're going to go about simplifying. How do you multiply fractions together? Multiply the numerators, multiply the denominators. So we would have cos times cos, which would be cos squared, okay? Notice I've been putting the squared on the cos, not the x, okay? Please make sure you do that. On the bottom, we'd have sine x times 1, which would be sine x. Alrighty, so now let's think. We've got kind of a whole number, I guess, plus a fraction. Think about if you had that just with numbers. If you had, say, something like 1 plus 2/3, okay, and you had to join those up into one thing, you would want to get a common denominator. So let's first make this a fraction by putting it over 1. And then our denominators would have to be the same. So with these numbers, we would end up multiplying top and bottom by 3. okay, so that we had the same denominator. Over here with our trig, we would end up multiplying the top and the bottom by cos x, because that, sorry, cos x, where am I getting that? By sine x. See, we have our denominator of sine x here. So sine x and sine x, whatever the denominator is. All right, that looks good. So let's rewrite that. Now that they're both over top of sine x, we can write it both over sine x, and we'd have sine times sine, which is sine squared, plus cos squared still, right? All right, now off to the formula sheet again. There is a Pythagorean identity that is exactly this, sine squared plus cos squared. So we know sine squared x plus cos squared x is equal to 1. So I can replace that numerator with 1, and then we'd have over sine x still. Oh, and that's on our formula sheet too, isn't it? 1 over sine x. 1 over sine x is known as cosecant x. So I can replace all of that with just cosecant x. And there we go. We're down to one single trig ratio. And that would be our answer for that one. Good. As you can see here, we're doing a lot of work with rational expressions, so I'm hoping everyone's up on their rational expressions. I'll try and show an example of each type of thing we do with numbers, just so it makes it look a little simpler. Okay, example 5. Express 2 tan a over 1 plus tan squared a. Notice they changed up the variable. It's okay, we can work with that. Just keep writing a instead of x. Okay, in terms of sine and cos, and write in simplest form. All right, that's not okay, we're not writing it in terms of sine and cos unless we need to, okay? So let's look at this expression. First of all, this squared is screaming at me as, hey, I'm on the formula sheet. 1 plus tan squared a. So whenever you see squareds, look for if it's one of your reciprocal or Pythagorean identities. So 1 plus tan squared on our formula sheet, doesn't matter that it's a or x or whatever, that's equal to secant squared. So I'm going to replace that with secant squared a. Keep the angle or the argument the same. Okay, now that we've made that look a little simpler, now's when I would write things in terms of sine and cos. Okay, but not before that because it didn't need to be complicated yet. Okay, so writing things in terms of sine and cos. Tan, okay, the 2 I'm going to put on top, sort of like 2 over 1, because I'm about to write tan as sine a over cos a. Again, that's on your formula sheet. Tan a equals sine a over cos a, so we're replacing that. And on the bottom, we've got secant squared, and we know that secant is 1 over cos. So if we square both sides, that really would just be 1 squared, which is 1 over cos squared. So secant squared a is really the same as 1 over cos squared a. So we're going to replace that here. All right, let's take this up. I'm going to multiply the 2 here just to make it look a little more simple. 2 sine a over cos a. Okay, notice the bottom is just 1 cos a. When you have a number like 2, it's not 2 over 2, it's 2 over 1. Okay, when you're working with fractions. Okay, now we have that. Well, do you guys remember the old adage, dividing by a fraction is the same as multiplying by the reciprocal of it? So we have basically this fraction divided by 1 over cos squared a, that fraction. So we're going to change that to 2 sine a over cos a, the top fraction, multiplied by the reciprocal of the bottom fraction, like that. Okay, another thing we can do is reduce any common factors in the numerator with the denominator. So if we're multiplying here, one of these coses, because really this is like cos a when you have cos squared a, one of those coses can go with that cos. And then what do we end up with? 2 sine a and then cos a. And we're not there yet, but that's actually an identity later on, a double angle identity that would be written as 2 sine a. But we haven't talked about that yet, so we'll stick with 2 sine a cos a. All right, good job. We only really have this last example, and I'll need to finish that up in the next video. So we will see you then.